Suppose we have these 4 transistors, which we control with circuits connected to the gate terminals. Each transistor either blocks current like an open switch or conducts current like a closed switch. Suppose we have 2 transistors blocking and 2 transistors conducting. The elevations represent the voltages of the different parts of the circuit. The arrows represent the positive current, which is in the opposite direction of electron current. Suppose we keep altering which 2 transistors are blocking and which 2 are conducting. The coil of wire represents an inductor. An inductor tries to keep the current flowing through it constant. Because the inductor is in series with the light bulb, the inductor prevents the current through the light bulb from changing instantaneously when the transistors are switched. The light bulb represents a load to which we wish to supply AC power. This light bulb behaves like a resistor in that the voltage drop across the light bulb is proportional to the current passing through it. When the current through the light bulb changes direction, the direction of the voltage drop across the light bulb also changes. Even though we only have a DC voltage source, we are now applying an AC current and an AC voltage to the light bulb. But it's not a perfect AC current waveform, since the current as a function of time looks like this. Since the voltage drop across the light bulb is proportional to the current, the waveform for the voltage drop across the light bulb also has this same shape. Suppose we want to make these voltage and current waveforms look more like ideal sine waves. We can do this by changing how we switch the transistors. Let us define the voltage on the left as VA, and define the voltage on the right as VB. So far, the difference between VA and VB as a function of time has looked like this. Let's change how we switch the transistors so that the difference between VA and VB as a function of time instead looks like this. The inductor acts like a low-pass filter, causing the current through the light bulb to look very similar to a sine wave. To reduce the ripple and make the output waveform look more like a perfect sine wave, we can increase the switching frequency thousands of times faster than what is shown here. However, with a switching frequency that fast, it would not be possible to see anything in the animation. This waveform shown here on the screen is something we can see in action in our circuit. This circuit is one of the many ways of creating an electric power inverter. An electric power inverter is a device that converts DC power into AC power. If the transistors behave like ideal switches, and if the coil behaves like an ideal inductor, then in theory, this circuit could be 100% efficient. This is because ideal switches and ideal inductors do not dissipate any energy as heat. Therefore, in theory, 100% of the energy exiting our DC voltage source could be delivered to our output, represented here as a light bulb. Of course, in reality, components are never ideal, and it's not possible to be 100% efficient, and some energy will be dissipated as heat in the transistors and in the inductor. But trying to be as efficient as possible is one of the goals of power electronics. More information about power electronics is available in the video Boost Converters and Buck Converters. Please subscribe for notifications when new videos are ready. Special thanks to all the people supporting us on Patreon. Your support is very much appreciated.